Thank you for the brief introductions. It is my honor to be here today to be able to talk to you about a research we've been doing for the past 6 years about combining machine learning and dynamical system together to try to learn or understand one of the most interesting natural behaviors called collective behaviors from observation data. Yeah, I would like to tell you how we can actually do that using machine learning. So here's an outline of my talk. I'm going to start out with the motivation. Why do we want to use machine learning to study dynamical systems? And based on that, how can we build up the framework to actually learn, infer these dynamical systems, and various extensions we've been taking with this project, and how to push it into more and more complex situations for learning these dynamical systems. And then I will give a brief summary of the stuff that we have done and been doing for the future directions. Okay. All right. So as we all know, machine learning is really good at recognizing patterns. And there are tons of interesting patterns that actually generated naturally that we can see every day. For example, these stripes on the zebras, these skin pigmentation patterns is actually really interesting. And these patterns doesn't need to be just lines. It can be spots, it can be curvy, it can be just patches. All of these skin static patterns that actually comes up naturally on animals, even on the skies. And patterns doesn't need to be static. It can be dynamic. So shown here is forming a finger-like patterns by this group of phototactic bacteria, meaning that they actually eat light as their food source, and they would move whenever you light a light source somewhere, and they move in this aggregated way and forming this kind of fingering-like patterns. And it can be also relatively static in this V-shaped pattern forming by a group of birds. And these patterns can be also really geometrically complicated, and this 3D spherical shape formed by a group of fish. And patterns can be also dynamic. For example, this is a group of starlings. This kind of behavior actually has a name. It calls murmurations of starlings. From a bird shape by a group of birds. So it's actually really interesting patterns you can form by all of these collective individuals, and they can just form these interesting patterns, and patterns can be changing all the time. For example, these ant bridges formed by these ants trying to cross over, and this bridge can increase in both size and the number of ants actually participating in this kind of bridge building. Okay. And humans have been demonstrating a lot of collective patterns. For example, this mysterious black building is a religious site, and you can see millions of thousands, hundreds of thousands of people just circulating around this black mysterious building. And they do it naturally. You don't need actually a conductor or anybody to tell them to move in that particular way. They would just circulate around this building all by themselves. Okay. In fact, patterns can be something a little bit abstract. For example, this is the light up pattern inside a monkey brain when they see certain images. And it shows out these fingering-like patterns, but only when they see certain images. This is done by connecting all of these different neurons, and it's really interesting to connect, to study this kind of pattern for connections of neurons and stuff like that. And patterns can be formed by a group of different features. For example, this is the synchronized fireflies. So you have a group of fireflies that flock, stay in place in the space at a fixed spatial patterns, and while they would light on and off at the same time, so they will have this synchronous behavior, all of these patterns. Okay, so we would like to understand that. And most importantly, we would like to be able to predict or control these kind of patterns. As it turns out, this pattern has a name. It's called collective behaviors. Sometimes they also call it self-organization, because it's just a group of agents, they just self naturally to organize into these global patterns. So as you can see, this is the definitions. You have some kind of global behavior emerges from a local interactions. So the key things here is that the pattern is global, meaning that is the whole system demonstrating this kind of behavior, but they get to this kind of global pattern or order using only local pairwise interactions. And no matter if the initial state is chaotic, you still will get this kind of pattern. So it's a little bit counterintuitive because it's against the second thermodynamics law. You actually have order emerging instead of having chaos emerging. This is what we want to do and what we want to actually study it. As it turns out, you can see all of these so-called collective patterns, behavior patterns in a lot of different areas. So for example, in physics, you have superconductivity. It can be considered as a global pattern because all of the particles actually points into same direction so that you can have the electrons flow in the same directions. In chemistry, in biology, we already see some of this flocking of birds. Social behavior of insects, we see the ant bridges. In sociology, human demonstrate certain collective patterns, group think, traffic flow. All of this are just one aspect of collective behaviors. Even in computer science, cybernetics, in linguistic, emergence of languages, you can think of it as a collective behavior. But you might say, well, why do we want to know that? Is because if we can actually understand, control or predict these kind of collective behaviors out of these individuals, we can actually do opinion analysis to study why consensus of political opinions can actually be formed. We can study social issues. You can use these kind of patterns to do particle swarm optimizations for high dimensional optimizations. You can also build these animal interactions into robots, into UAVs, so they would behave naturally to avoid dangers. And you can actually have the least amount of control you can have of these robots, and they will still move naturally. So that's what we want to do. All right. So how we can actually put a math model onto these interacting system of agents so that they will demonstrate these collective behaviors. It's actually really simple. As long as you allow them to interact pairwise, you will as A1 to influence only those close to them, A2. And you can have different types of agents. It doesn't really matter whether these agents are of the same type. You can even have these agents interact with the environment. And eventually, under some kind of interaction functions interaction rule, you can actually have these collective behaviors, it's global patterns. One of these famous models is called the Boyd model by Quick Reynolds. It's actually not a professor, but yeah. His Boyd model actually was developed, deployed in the, I forgot which Batman movie, but he actually got an academic award for this Boyd model. It's actually really simple physical model. It follows a basic 3 zoom principle that if the agents get close, they should repulse to stay at a certain distance. If they're too far away, then they should attract so that they can stay in the whole group. If they're in the middle range, and they should align. They should align the heading so that the whole group will stay as a whole group and fly at the same velocity. So that's the basic flocking model he proposed. This kind of principles, we as a mathematician, we don't just come up with them randomly. We actually base these principles on experimental data. As it turns out, it actually follows what the actual birds are doing. There's also other models by Bertozzi's group using self-propelling particles, telling how fish will swing, form patterns in the oceans. Weishek and Kuka-Smell have the flocking of birds models. Krauss has the opinion dynamics model, studying how opinions is formed, and all of this different stuff on how collective patterns is actually formed. But what we want to do is, can I just look up in the sky, see how the birds are actually moving, and give you a model, a math model, for you to actually control and predict the movement of these agents in these interacting agents. That's what we are doing with this approach. Okay, so I'm gonna go really quick on the references. These are all the different models we use for our learning approach. And here is a list of paper we actually produced with this learning approach. I wanted to point out that our learning approach is a little bit different from Cindy. We use all the modeling and the physics-informed neural networks, which is called PIN and neural ODEs. It's because we actually look into the dynamical systems and do a little bit dimension reduction with it, which I will mention what do I mean by dimension reductions. And we have been going to a lot of different directions with this approach. Okay, all right. So now we're ready to talk about how to actually learn this dynamical system so that you can produce a dynamical system to explain this observation data. Back to the question I asked, while we are not actually learning the whole dynamical system, I'm actually learning just the rule on how agents would influence each other so that overall you get the global pattern, okay? And I want my models to be physically interpretable. I want to give you something that you can understand. And not just a bunch of parameters. It can be, it also has to be effective, meaning that I can apply it to as many difficult dynamical systems as possible, different dynamical systems as possible, and also efficient, that I can actually apply my learning on large set of data, and I can learn like linearly, or even I can learn it on my laptop, okay? All right, so to consider that, I want to set up a really simple system that we can lay down the learning principles for. So we're going to consider a system of n agents, and each agent is assigned a state vector called xi, and the xi can represent different things. It can be positions, it can be emotions, it can be wealth, it can be anything that you can throw at these agents to describe this state or behavior. Most importantly, I want the change of the state of these agents to kind of follow the so-called least action principle, because we are always optimizing. I wanted to kind of preserve, to save energy. So it goes into the negative gradient of certain system energy. So we are always saving energy, okay? But we're not gonna use any energy on this whole system, because we know from biological experiments and physical experiments, we know this certain energy has certain form, and we want to preserve it. So we're going to consider that the system energy is just a sum of pairwise potential based on pairwise distance of the states. Okay, if I simplify, then I have a first order model, really simple first order model, that the change of the state for each agent is an average sum of a certain function, which I will give it a name, that based on the pairwise distance of the state and weighted by the pairwise differences. Okay, it's a really simple model, but you can have a lot of different patterns out of it. And then we call this particular function the so-called interaction kernel interaction law, meaning that it governs how agent X prime would actually influence agent I into moving into the next step. Okay, and in this case, there is a pairwise distance variable, which I will talk about it. Why do I mean it by pairwise distance? You can actually generalize and take off this restriction at a later stage. Okay, and if I know this interaction kernel, I can induce patterns. I can induce crystal formations. I can induce clustering of opinions if I put a certain properties on the feed. For example, if I let feed be compactly supported or posited, but only have values up to 1, then it actually forces all the opinions to form clusters. Okay, and if it's greater enough, then all these different opinions will just form one cluster, so you have consensus. Okay, all right. And if I have phi be globally behave but decay really fast towards the end, then you actually have flocking. So at the end, it shows that they all fly in the same velocity, not just same speed and also directions. Okay. And if I have these flocking has a really complicated kernels, then they actually eventually would do flocking around center of mass velocity. So it's not just flocking, there's also some kind of swirling. Okay, so different fees, you have different patterns. Okay, all right. Okay, you can even put an additional assumption on it so that not only would they flock, they will also form lines. Okay, this is exactly what the V shape, we are close to that, not yet then. Okay, the V shape of flocking of birds. Okay, so what I wanted to ask is, if I'm given the observation of these trajectories, can I learn the interactions that tell me how the agents are influencing each other? This is my questions, okay? All right, so in order to answer that, let's just vectorize everything, put everything into one big vectors, put all the states into one, put all the right-hand side into one. Then as it turns out, the whole thing looks like a regression problem. I'm just having a observation of the state. I have the derivative of the state, but the observations of the state is the independent, the derivative is the dependent. So I'm just finding a function to match the two together. So it simply looks like a regression functions. However, if you look at, so this is the convergence rate for regression review. If you look at the dimension of all my observation data, this is a high dimensional data, because not only I have a large number of possible large number of agents in the system, the state, the length of each state vector can be also large, because you can describe a lot of things with the state. Okay, so with that, you can see that my convergence rate is going to drop to basically 1. That means I have no convergence rate at all if I just go with the normal regressions. Okay, not to mention the data is not independent, so we cannot do regressions. We cannot even do neural network because it's a high dimensional data. Okay, so we need to go back and look at the right-hand side, because the right-hand side is not just any right-hand side, it is a special right-hand side. Okay, so with that, I'm going to assume not only I have observation data of the trajectories that correspond to different time, I also have it correspond to different initial conditions. Then, like all the machine learning method that we do, we design the loss. So I'm going to design the loss of what I can observe for the derivatives, what I can predict based on this right-hand side. Remember, this right-hand side is a sum of all of these interaction functions. Okay, and I want the difference between what I would predict based on this right-hand side to what I can observe at any time and any initial conditions. That's what I want to design my loss functions. Okay, so in this case, because you're always searching your loss function over a really nice space, you have a minimizer. The only thing left is that, can I show the minimizer that I obtain from this kind of loss that will go to the unknown interaction kernels? Okay. And as it turns out, to do it in one step is not that easy. So we take the expected version of it, like what we always do with math problems. We always take the continuous versions and show the continuous version going to the unknown interaction kernel. Okay, because it's really easy to show the discrete one and using the law of large number with that kind of convergence. All right, okay, but to show that one, we need additional conditions. I'm going to skip on this. This is basically, you can think of it as that. So you can think of it, this is the loss that I'm actually trying to minimize. It actually bounded below by the distance between what I actually want to learn to what I actually putting there. So you can think of it, I'm minimizing a loss, I'm actually minimizing that distance. So this is the condition that I put on. Once I have this condition, then I will have both the convergence of my minimizer to the unknown interactions and the predicted trajectories. So this x hat here is what I evolved from my phi hat. Okay. All right. So I want to point out the rate is optimal and independent of the observation data, the dimension of the observation data. So we basically have a dimension reduction there, because no matter how high your observation data is, I can always learn it as m to the negative 1/3 rate. Okay, it's independent of the dimensions. Okay, and we have a software package. This is totally open source. However, it's based on MATLAB, but you can try it out yourself. I actually, if I have time, I'll do a quick demo of this software package. All right, okay. So let me show you some results. Quickly show you this opinion dynamics. So this is the evolutions of the opinions. The black dashed lines, this is what we actually learned. So we learn only from 0 to 10. After that, everything is predicted. If they're on the same row, they share the same initial conditions. The trajectories on the left, these are the true trajectories, meaning that this evolved from the unknown interaction kernel. The trajectories on the right, those are actually evolved from the learned interaction kernels. As you can see, we can actually preserve at least 2 digits accuracy out of a learning approach. Not only that, after you learn from predict after the learning time 10 seconds, we can also preserve the formation of the clusters. Okay, at large times. Okay, and I want to point out that so the first row is only taking from the training data. So I mean that the initial condition we already seen that, but the last row, this is the initial condition that we have not seen. Okay, in fact, this is a system of 20. Actually, this is 40 agents. So we learn from a system of 20 agents, but because we're learning interaction kernel, we don't need to retrain. We can use it and apply to system of 40 agents right away because of the independence of the kernel, because we are learning the structure of the system, not just the original right-hand side. So we can do that. Here's a comparison of the true interaction kernel versus what we actually learn. We do not let the code know that the kernel is actually compactly supported. We don't let the program know that the kernel is actually discontinuous. This is all learned from the data. So this actually, which is why the range is actually up to 10, because we just learned it from the data. Okay. All right, so now we are ready to extend this approach, this really simple approach, from a really simple first-order homogeneous agent systems to a lot of more complex, more complicated systems. For one thing is that I'm only consider homogeneous agent, meaning that agent doesn't have any particular type. They're all the same. It's not the true if you consider that kind of system in real life, because agents will have different types. You have leader and follower, you have pedestrian vehicles, you have criminals, normal people, you have predator and prey, you have way more different types in the actual applications. So I'm gonna build the type information into my systems. So now we extend the fee, not only depends on the pairwise distance between the states, they also depends on the type information. So that means that if an agent is of a different type, this fee is going to be different. Okay. For example, if I have two types, type 1 is a leader, type 2 is a follower, then for an agent in the leader group to have a different interactions on a follower group than from itself onto the leader group. So that's why you will have a different fees based on not only just pairwise distance, but also different types, type to type interactions. So if you have two types, you will end up with the 2 square different interactions, 4 different interactions. Okay, so here's an example of extending this idea to the predator-prey systems when you have a single predator chasing a group of prey. So 2 types. Again, on the left, these are all true dynamics. On the right, these are all learned dynamics. So we still preserve some of these qualitative behaviors and also have a relative accuracy good enough to actually predict into a long time. All right, and because you have 2 types, you have a total of 4 different interactions. So this one on the upper left, this is the prey on prey interactions. The upper right is predator on prey. So predator is pushing the prey. He's always scaring the prey away. Okay, and the lower left, this is prey on predator. So prey always attracts predator because the predator want to eat the prey. And because there's only a single predator, so there's no way we can learn a predator on predator interactions. There's no more data we can learn. Okay, so here's a comparison of these interactions. So that's the first thing, building the type information into the systems. Another thing is that I show you the first order when the change of the state is only the first time change. That's not going to be that realistic. So we're going to increase the order of the derivative. Not only that, we're also going to consider 2 different types of interactions. The first one, we call it the phi because you can actually derive this kind of interactions from energy. So it's like energy based because they change it only relative positions. The second one is called phi because it changes your headings, the velocity. So that's why you actually need to consider both the possible change of energy base, which will repulse or attract you, and the alignment base, which you would just correct the headings. So we have both the mid-range, long-range, and short-range interactions, or 3-range interactions into the second-order systems, okay? So I already said that. So here is a comparison of that flocking model we talked about when you anticipate the future positions of your neighbors. So you don't flock at the same time. You are just swirling around a center of axis and then eventually flock at the end. So again, on the left is what we actually predict using the true interactions. On the right is what actually learn the trajectory learn from the learn interactions. Okay. All right. You can also do these so-called double meaning examples when this group of fish will half of them swing clockwise, the other half swing counterclockwise. And we can also learn from these interactions and preserve at the large time. So this is actually predicting into 5T into the futures. And then with that, the errors is going to big, but the qualitative behaviors that the group is still half of them swimming clockwise, the other half counterclockwise, you still can see that behavior preserved in our learning systems. Our interaction kernel can actually preserve that. That's what we did. All right, okay. I'm going to go a little bit quicker on the manifold case because all these examples that I show you, these data represent a 3D Euclidean positions. So it's actually natural to think they should be a Euclidean distance. However, if you're thinking about different data set, if the data is not just position data, it might be images, it might be something else, so that they don't necessarily live in a Euclidean space, then you actually need to build a manifold to actually respect that kind of geometry. And with that kind of geometry, we are still able to learn as long as you build the knowledge. So here, as you can see, we actually change the norm from a Euclidean norm to a manifold norm, meaning that we respect that geometry. So if you respect the geometry, then you get the same learning rate. You can still learn as good as if they're actually in Euclidean space. So this is an example of a single predator chasing a group of prey, as if they're actually running on the moon. So this is what they would behave. Okay, we can actually predict both the behavior within the learning time and into the long time. Okay, all right. Well, so all of the examples I show you, these are from simulated data, meaning that this data we simulate, they are not real data, they are not from real life data. And you probably wonder how good is your learning method if you actually can do it. Can you actually do it for real life applications data? So we tried that. It's really difficult to actually study birds flocking because it's really difficult to identify them. If you have only 10 birds, yeah. But if you have 1,000 birds, this is literally impossible. All right, so we take the most easy data that we can take from NASA JPLs, which is a solar system data. It is not really observational. It is in some sense because it actually put down about 2,000 years of true observational data, but it's a really, really accurate synthetic data that uses Einstein general relativity. It's so accurate that the moon landing mission actually uses their JPL data. So we consider it to be true data because it's so accurate. Okay, so this upper left here is the JPL data that we have. We took this data from JPL. We took about 500 years of daily observations of the moon and the sun and the earth, 8 major planets, and studied them. So this is what we have from the learning dynamics. This is what we have from our learning examples. EIH stands for the Einstein-Infeld-Hoffman method. This is the, actually it's not the general relativity. This is the first order approximation of general relativity. And Newton is the good old Newton, the good old universal law of gravitational systems. So we compare them, okay? As you can see, there's no eyeball norm, there's no difference, okay? Okay. In fact, under our assumptions, this thing is so accurate. Do I have an example? The prediction of this trajectory is so accurate, we can actually look into the most sensitive term from the astrophysics, astronomy side. It's called the perihelion precession rate. That term is so sensitive and so small. That's actually how Einstein proved that his general relativity is correct. We can actually look at that. I forgot a slide, but we look at that and we can actually produce something so close to the original Einstein's. Okay, so this is the comparison of the real data that we have. All right, as you can see, as I zoom out a little bit more and more, our system behaves more or less similar to Newton's. Because that's the drawback. We do not have the general relativity term. the EIH actually have the general relativity term, so they can predict better. Us is constrained by the framework that we actually put down. So, which is why we look like Newton. And then you might wonder, what's the point? Because you already have Newton, you already have Einstein. Why would you want to do that? The reason why we want to do that is because we want to know, without giving computer assumptions. In this case, I'm only fitting trajectory data, meaning only point-wise positions, velocity of the planets. Without telling them what the system would behave, the computer just tell me they would just run into these elliptical trajectories, meaning that the computer discovered what Newton does over the course of what? I think he spent about 10 years on actually proving that 1 over r squared is the form of the general law of gravitation. So, and the computer did it just without under 30 minutes, okay? And actually, it's more accurate than Newton did. So we're actually trying to see if we can teach computer physics, okay? All right, so that's that, all right? Another thing is that I've been emphasizing on the system should depend on pairwise state. They might wonder, is it true? Because if you look at birds, how birds will interact or influence each other, well, they kind of have a sense of distances. They kind of know that some other birds is close to them, but they also have the so-called limited visions, right? You can only see ahead of you, and those birds behind you, you wouldn't be able to see and you wouldn't be able to feel, okay? So pairwise distance might not be enough to actually describe the whole dynamical patterns and behaviors. So what we want to do is that, well, the reason why we use pairwise distance is because it has some kind of symmetry, it has some kind of invariances, but can we actually lessen that restrictions? Can we actually get rid of these pairwise distance assumptions? So we push it a little bit further. However, so we take off the assumptions that everything depends on pairwise distance, but we let it become everything depends on pairwise of states. The reason why we still use pairwise is because remember the definition of collective patterns is local interactions. So we still need pairwise, okay? So, but we don't know how they will interact. I just need the states, okay? So I'm gonna lessen them. So if I do that, I'm going from one-dimensional functions, so the little phi here depend only on one variable. However, the state, remember the state here is at least d dimensions, so I'm going from one-dimensional function to a 2D dimension function learning. So I'm actually increasing my dimensions of learning. I'm increasing the difficulty, okay? But I can learn more because I lessen these restrictions, okay? So, but if you want to do that, you need to do dimension reductions. Because, for example, if little d is just 2, you're going from 1 dimension to 4 dimension. It sounds like, well, yeah, this is okay. But if you want to learn approximate one-dimensional functions using 100 points, then you get 1 over square root of 100 accuracy. But if you do 100 points for 4-dimensional, you won't get the accuracy. You need to do 100 to the 4th power. That give you what, 100,000, close to 1 million points in order to learn 4-dimensional functions. So even if it's low as 4, it's really difficult to actually approximate and learn, okay? So that's why we want to do a dimension reductions with this approach. So we're actually able to actually learn both the interaction variable, so I didn't put it here, is that we actually, so we have a way to actually enlarge the dimensions, but we can project it down to a low dimensional manifold so that we learn both the interaction kernel and the projections, and then you can learn it efficiently. So we can actually do both of this kind of learning. And then we're able to produce both the trajectories, again, because we are learning interaction kernels, so we can actually put it onto a system of 20 agents, and it just behave roughly the same, okay? All right, so that's that, all right? So all of these examples I showed you, they actually learn on a series of time series data. You actually need to take a series of time snapshots of the whole system and then produce a dynamical system to actually do predictions and control. Okay, what they're showing here is a settled down systems. Everything is already settled down to a steady state. I only have one picture. Can actually produce the kernel that tell me how I actually get to this ring of agents. Okay, this is what I wanted to do. Okay, as it turns out, this kind of learning is really ill conditions. So that's why you only learn up to functions, up to certain constants. So we're able to produce something really close. Okay, you take out the ill conditioning. Okay, the reason why I want to do that is because if you look at crystals, they already settle down to steady state. There's no dynamics there. They only have one pictures. So this is why we want to do a steady state learning. One snapshot, are you able to still produce the interactions to actually tell what's happening with these systems, okay? So that you can reproduce or control this kind of patterns of behaviors, okay? All right, so as a summary, I have shown you how to actually reconstruct the dynamic system for our observation data effectively because, and also efficiently. Our algorithm is also stable because we already use it for many different kinds of systems, and also efficient shown by our approach. And I also show you the many different extensions we take for many different complex systems. For future work, we already studied is what if I have noise into the systems, especially stochastic noise? So the system becomes stochastic. Can I still learn? We have made some progress in there. There's already work on lower dimensional SDE examples that we actually use in financial math models. We actually have some examples. What if the data that given to me, so we have the manifold data, right? I don't tell you the manifold. Can you actually also learn the geometry where these agents are actually lying on and the dynamics that tell how would they change into the futures? So we are actually working a little bit onto that direction a little bit using LTSA and isomath to actually learn the geometry and then with that to actually learn the dynamics. Okay. There's also remember the equation that I'm showing you is 1 over n, right? This is 1 over n. This is called arithmetic averaging. But for birds, they don't know how to count the number of agents into the whole system. So it shouldn't be 1 over n. It should be something else. So, which is why I put it out here. It's called topological averaging, meaning that the birds will have sense of density. So if they are in a really dense area, they should move slowly. If they're in a really not so dense area, they should move fast. So can I actually learn that density idea, the sense of density into this model and then let the data tell me whether these agents are following this kind of averaging instead of arithmetic averaging. Another thing is for the agent type, the example I showed you is that I already know the agent type. I already know that there's one predator chasing a group of prey. But if you look up into the sky, look up anything you observe, you don't have the agent type information. Can you actually learn that type information after just looking at the, say, CCTV videos? Then you can tell which one is the bad guy chasing a group of good guys, okay? Can we actually do that? And also this multi-physics examples is, I showed you the example of learning gravity, but what if I have gravity and electromagnetic forces and all the other forces that we have, fluid forces that we have, can I actually decouple them and learn all of these different forces all together, okay? So with that, I conclude and thank you. Questions? I was going a little bit fast towards the end.